Today I'm focusing on how working with geospatial data on Databricks makes sense, especially when it comes to versatility, scalability, and openness. So, question, what makes Databricks good for both large and small geospatial workloads? So if you follow this slide here from left to right, I want to highlight the ability for you to run any of your favorite geospatial libraries, especially like Python libraries, you can just pip install on Databricks. You can pip install GeoPandas to work with geometry data types, Shapely for your polygons, raster.io for importing raster data, or even install GDAL and all its OS dependencies and work all on that on Databricks Spark clusters. These libraries work on a single node cluster in Databricks like you would on any other Python environment, or you can wrap these single threaded functions in Spark user-defined functions because Databricks leverages Spark for distributed parallel processing. So you can kind of take these and supercharge them by wrapping them in Spark UDFs on top of your data. The middle section of this slide here are Spark-specific geospatial libraries. You can easily install and use on Databricks as well. These are like your Apache Sedona, GeoMesa. The middle one is a Databricks lab project called Mosaic for geospatial. And these kind of are native to Spark. So they work a little more efficiently and are more scalable even than the initial single-threaded libraries that you can wrap in Spark UDFs. But finally, on the right side, right, that's where we're going with these geospatial capabilities built into the Databricks product by Databricks engineers. So these are blazing fast. They leverage Photon, which is our even faster Spark engine that Databricks runs on, and give you things like all the SQL ST functions you know and love, and H3 functions for gridding and really fast retrieval. Again, you can use any combination of these or interweave them as necessary to achieve all your goals. Additionally, I want to highlight, because I know a lot of people on this call use ArcGIS regularly, that Databricks does have connections and a relationship with Esri. We have Esri Geospatial Analytics engine, which is installable on our Spark clusters. But additionally, Databricks is currently working with Esri to approve Databricks as a cloud data warehouse connector to ArcGIS. So the backend workload can all run on Databricks, and the data can live, if it's running on Databricks, the data can live next to the rest of your data estate for other purposes like building AI/ML models in Databricks and correlating it with other data. So you're not just siloing your data in like ArcGIS and Esri and then having the rest of your data sit over in Databricks. They can be side by side. And so Esri has given us initial feedback for our suite of ST functions. We're actively iterating and working with them to get their changes incorporated. And hopefully it won't be too long before Databricks is that kind of certified connector piece there. So what does the current state of built-in geospatial capabilities in the Databricks runtime look like? Like this is the far right side of that distributed data journey slide I showed. So we have over 30 H3 functions, over 75 spatial SQL functions, initial support for GeoHash, and you're able to access these functions in notebooks, which is the regular general development interface for Databricks. Those use Spark clusters, or you can use them in our DB SQL editor. So this is attaching to a SQL warehouse and running SQL queries the way you would expect to do that on other SQL warehouses. Also, we work very closely with lots of libraries and platforms. We're very open, versatile. So like your Esri and Carto, leading cloud-based geospatial platforms, we integrate well with them as well. So how does geospatial slot in with the rest of your data estate in Databricks? So we like to think of geospatial as just another file format or data type, the same way we do with all the other structured and unstructured data in your lakehouse. So you can ingest data in a multitude of different ways, whether it's streaming, downloading one-offs, connecting to other databases to bring your data into Databricks. And then you can store that data in volumes or write them to Delta tables, which are the most efficient way of working with data in Databricks. Once that raw data connection is made, you can also orchestrate all this work and automate it using Databricks jobs the way you would with any other ingestion data flow pipeline you would on Databricks. Or you can experiment and build AI/ML models on top of your geo and non-geo data kind of combined, or do any other kind of scalable analysis using your favorite geospatial libraries. So kind of like to highlight that orange bar. Like you can always still use your favorite geospatial libraries in here. And finally, you can flexibly visualize or build applications on top of your data that you develop in your notebooks, or serve them via endpoints, dashboards, or fully customizable Databricks apps, or connect to these third-party platforms on the right side of the slide, like ArcGIS, Carto, Tableau, or Kepler. To touch really quickly on some of the Databricks visualization tools. So obviously, if you work in notebooks, you can visualize the same way you would in Jupyter notebooks. But you can also build out simple map visualizations in dashboards using Databricks AI/BI. This is the Databricks native dashboarding capability. And we call it AI/BI because we allow you to build visualizations in your dashboard through natural language. So this would like creating a map, plotting data. You could say, basically type in, create a map, plotting data from table X and circles, or their size by column Y of that table. And it could come up with this for you and kind of build that out. Very similar to the experience you would have in Tableau, except with the kind of that natural language capability built into it. Now for a fully custom experience, you can build and host web applications on top of Databricks. And this is what we're going to do today as part of our demo. So Databricks, and we call this Databricks apps. Databricks apps allows you to build any application and has first-party support for like Python frameworks such as Plotly Dash, Gradio, Streamlit, Flask. And because it runs directly in your Databricks workspace, it can be governed by Unity Catalog and use the same user authentication and authorization, treated exactly like anything else in your Databricks workspace. So it super easily then connects like on the back end to SQL Warehouse compute, cluster compute, and model serving endpoints, and any other external web services you need to call, like in this case, Mapbox layers and that kind of thing. You can treat it like you would any other web application that you're building, except it can live and run in your Databricks workspace.
Just had a quick question on that from the webinar audience. So if I have an existing custom application or some sort of internal app, how hard is it to move it to Databricks or use it in Databricks right now?
So it's pretty easy to move. I'll give when we go into the demo, I'm going to hop quickly and kind of show you. But essentially, you just have a directory that contains the same files that you have for your current web application. Like in this case, it's like an app.py, an app.yaml file, and like the requirements. So if you just get it into that format, but it's essentially just your app.py, you do that and you help build your environment out. And I'll show you exactly how we're going to do that. It's a pretty easy port over one-to-one, right? It just builds it out using the same like web build tools that you are using externally if you're running like a local application or one on another server.
Got it. Okay. Sounds like it's fairly straightforward to lift and shift then.
Yeah, it shouldn't be too bad. So to move from visualization now to like backward into the data processing part, I kind of want to give a quick insight before we jump into the demo of how we approach scalability on Databricks with ever increasing geospatial data sizes. So at Databricks, so when you see this decision tree here at Databricks, you have access to both sides of this, but you might have to make some decisions based on data size, precision, and desired latency, like how accurate you want to be versus how fast you want to be. And you can see here that we kind of categorize this into spatial binning techniques like H3 and pure vector spatial analytics using polygons and like your ST functions. And to think about how the decision flow chart looks visually, like this slide, I think really works well. And we look at like as you try to speed up and scale spatial joins and filtering from polygons that you might have. We kind of think of this as like the fastest is on the left. So this is H3 binning. So if you create like an H3 cover of your entire polygon, you're able to do really, really, really fast. It's like over 90x gains versus just doing straight up polygons. So you can do this. But of course, you lose precision at the edges in this case. If you hop all the way over to the right, this is the slowest approach, but you obviously get the most accurate results with your ST functions looking at polygons. So we have built-in H3, accelerated capabilities for the one. We have ST functions that work really quickly with the other, but we also have functionality to do this hybrid approach in the middle, where you look at essentially what H3 hexes appear in the core of the polygon. And then you look at the ones that appear on the edges and you do vector filtering only for the edges. We're not going to touch on this too much in the demo, but I just kind of wanted to give you an idea of the flexibility and scalability of the platform and how we think about this internally when we're looking at these large scale problems, right? This also works for raster data, which can be ingested and converted into different bin resolutions using H3. So you can really process that and analyze like really big, cumbersome raster files faster, especially if you can say, I can aggregate up to a higher resolution level or a lower resolution level with H3. So these next couple slides just kind of look at, okay, these are could be like 1.5 seconds to look at each one of these, the spatial SQL functions that are still in preview right now, but are available upon request that we're working into this and like helping to supply like, again, that backend for Esri. So we've got 75 of these just to kind of show you the coverage that we have here with spatial SQL functions. So now we're going to pivot over to the demonstration. So we're going to take a quick look into some of the ways you can work with geospatial data on Databricks in this demo. The use case we've identified, Keenan kind of hinted at it, is based off of publicly available data on the U.S. Fish and Wildlife Service webpage, with data on the range, so like the geospatial coverage of every animal, fish, plant species covered by the service. The challenge is you download that huge data set, and each one of the records contains massive, massive multi-polygon and polygon strings that are super duper long, incredibly cumbersome to deal with, or to prep for any like additional visualization, or to work with from an analysis perspective without getting into like these huge like memory issues when it comes to super duper long strings for these multi-polygons. So what we're going to try to do is show you how we can download that data into a Databricks volume, which is essentially cloud storage on Databricks, but it's governed cloud storage. Unpack it, load it into a notebook for analysis, and run a combination of spatial SQL and PySpark functions to break up those multi-polygons into usable individual polygons, and to create H3 hexagon indexes to aid for quick retrieval and future binning analysis. And then we're going to look at how easy it is to automate that process, how you can access this data, and how we can build that Databricks app using Plotly Dash and Kepler GL to quickly pull and visualize the data. And we might also throw in a little bit of generative AI because I like to toss that into every every demo that we do. Because who doesn't love Gen AI right now, right? Okay, so let's hop over. So first thing I want to show is this is kind of where we're pulling the data. There's just a giant zip file download that you can download for all of these species from the Fish and Wildlife Service webpage. So when we hop over to Databricks, I know some of you have worked in Databricks, some have not. So just like the fastest possible intro to Databricks you could possibly see. This is kind of your landing page, but the main look, especially from a persona perspective, is this left bar over here. Workspace is going to be looking at basically where all of your files and notebooks and other things exist from a development standpoint. So this is my like workspace with directory structures. Catalog is going to be your where all of your data, machine learning models, functions, volumes, all of that resides. And it appears on the left like very much like you're used to seeing with a traditional database. However, you can look to see like everything is managed through Unity Catalog alongside of each other, including AI/ML models, functions, volumes, tables, that kind of thing. Workflows is our orchestration and automation platform. Compute is where you actually, because in Databricks, compute is always separated from storage. So you can spin up any type of compute that you need from a Spark cluster or SQL warehouse or anything that then accesses the data in place in cloud storage, such that a SQL warehouse or cluster or multiple clusters can all access the data without bumping into each other in the same way. And then you can also store all of your data at like cloud storage costs and run compute on it up here. So key thing to always remember at Databricks is that your compute and your storage is separate. So you're never stepping on anybody's toes as you're doing this, and you can have multiple people accessing the data all in one place. So this like single source of truth data that's underlying it. Then the SQL section here is where you think of this as like a traditional, what you think of it like a data warehouse, right? Um, so you can spin up a SQL editor, run queries in here, but these queries aren't hitting database tables as much as they are hitting Delta tables stored in cloud storage. So it's kind of a paradigm shift mentally to think about it that way. But this appears, mentally the same way you would expect any other SQL platform to look. From data engineering, this is kind of where like a lot of the orchestration happens with streaming pipelines, data ingestion, workflows, that kind of thing. And then from a machine learning AI ML perspective for data scientists, we have things like feature store tables, model repositories through MLflow, model serving in this place too. So all of this stuff and your generative AI playground is all available here. All kind of on this left side is kind of your conduit to all of it. So what we're going to do first, right, is hop over to look at exactly how we're downloading that data and storing it and where it appears once we've done that in Databricks, right? So we'll hop over. If I go into my workspace, I'll go into a couple folders down here, Geospatial DOI Workshop, and go to my DOI data download notebook. So again, like I said, most of the time when you're interacting and developing on Databricks, it's in notebooks. There are a lot of other options. There's the SQL editor that you can write SQL scripts in here and run those separately. But generally speaking, you interact with notebooks, which basically are Jupyter notebooks if you're used to working in those two with some added capabilities like built into it. But you'd be very familiar with it if you work in Jupyter notebooks. Um, so in this case, essentially what we can do is set this, and you can run %sh commands to do Linux commands within your notebook, because naturally these are in any of these languages, Python, Markdown, SQL, Scala, R. And I'll get into exactly bouncing back and forth between these and notebooks a little bit later. But we can reach out, and this is the location of the zip file, and store that in a Databricks volume, which the schema goes our catalog and schema species range. And then we can also run a command to unzip this as well to show where this is going. So I talk about a lot about volumes, right? So if we go over to catalog, and where we're operating is in Justin M is the catalog, and our DOI webinar is our schema. And we can see that we have tables and volumes here. So we'll look at the tables a little bit later. But volumes we declared that here in our catalog, schema, species range is where we wanted to download that. So we have our volume, which is our catalog, Justin M, schema, DOI webinar, and species range is our volume. You can see that's where the zip file appears. And then as we unzip it, you can treat it just like a Linux file structure. And it unpacks all of our data here, our shape files, into a directory underneath of that volume. So that's how we kind of get the data in here from a, for lack of a better word, odd file type, like a shape file, right? If this were a CSV, you could ingest this directly into a Delta table or Parquet file, or any of those types of things can obviously stream through any of these things. But for kind of a less traditional thing like a shape file, like a lot of times you can bring it over into a volume and read it in from there. So let's do that. So as we back out of this and we go to our DOI massive multi-polygons, where most of the work is going to be done here, notebook, you can see that, again, this looks like a traditional Jupyter notebook. You can pip install whatever libraries you want in here. Obviously, we're running in Python, but we can pip install whatever Python libraries you need. Do things like set your catalog and schema, so you have that through the rest of the time, and run each one of these cells throughout the process. So again, we've identified our zip file, which exists in our volume catalog schema, species range, and the name of the zip file, and our layers within that zip file. We can read that directly in, again, like I said, with all of your favorite geospatial uh, Python geospatial libraries like GeoPandas, right? So we can actually read this shape file from the zip file in GeoPandas and take a look at that. We're able to display this basically because they truncate these multi-polygons when they're displaying it to you. So these things are outrageously long and super difficult to deal with. So we want to deconstruct those. Um, to give a quick example of like how long and difficult these are, this is if I were to just try to display the full data frame, I get a results too large. Can't even display the multi-polygons in the notebook. Can't download them from certain pages. Even if I download it and unzip it on my laptop, and try to view the individual multi-polygons just as text files in VS Code. So this is literally, I'm going to export a multi-polygon and it's so big and so much text that I'm getting like crash errors in VS Code on my laptop. And I have a pretty beefy laptop, so that goes to show you what's going on. Very difficult to work with. The idea of like um, trying to do anything at scale or a process of this would be kind of a pain. So what are we going to do? We want to take this GeoPanda. Now that we've read into GeoPandas, we want to convert the geometry data types into strings, load that into a Spark data frame, and work with the power of Spark to kind of unpack and recalibrate these into standard polygons. So we make this a really long skinny table as opposed to a wide with a super duper long multi-polygon string at the end table. So how do we go about doing that? You can run your favorite GeoPandas commands, right? So we're going to convert the um, geometry data type to WKT and like spit that back out here. That turns this GeoPandas data frame essentially into a Pandas standard data frame. And that then becomes super duper easy. You don't even need this. This is optional schema of it, but you can literally just do species data frame and create a Spark data frame off of your Pandas data frame in one line like that. It's super duper easy to bounce back and forth between things like Pandas and Spark data frames and Pandas on Spark. It's like a one line for each one as you're going through. So a lot of times people say, oh, working in Spark is difficult. Databricks is on Spark. I don't want to learn PySpark. Spark is super hard to use under the hood. Well, it really is. It's super easy to take a Spark data frame, convert it to pandas, and just do everything in pandas if you wanted to, or do pandas on Spark, where you can do distributed pandas and then use that to write back to your file. So just a kind of a disclaimer that it's really not as difficult as you might think to start working in PySpark. It's become a lot easier over the course of the last 10 years, right? So now that our data is in a Spark data frame, we want to write that out to a Delta table in Databricks. So A is persistent, and B, now if we do that, we can utilize SQL, PySpark, and like PySpark combined with SQL, and just show you the versatility of working in here from those two language standpoints. So what we do right here is after loading it into a Spark data frame, we can super easily write it out to a table in our catalog. So this is, again, those giant multi-polygons, but now they're stored as strings. And we can write that out to, by running this line, write it out to our catalog schema and DOI species raw. So let's hop over to our catalog again and see where that shows up. So our catalog is just an M, schema DOI webinar, and we end up with this DOI species raw table. So what you're able to see, there's a lot of information about the table. One of the cool things, and this isn't even the Gen AI piece I was going to talk about, but one of the really cool things for all the tables that are stored within Databricks, you get stuff like using Gen AI to do a automated description of the table. So you think about this as like documenting your data versus not documenting. This automatically can document by looking at the columns and looking at like the first row of the table to see what is contained in it and do it that way. You can also use a button right here so you can do this, hit accept, and all of a sudden now you have a well-documented table. And after hitting this button, it looks at each single one of these column names too and creates a uh, description using Gen AI model for each one of these. So you can literally go from like completely undocumented, like most of our tables look like, to super well documented from a description and uh, column field in that case. So just a really cool like example of how Gen AI is kind of like injected it across the entire data intelligence platform of Databricks.
Justin, am I going back to that real quick? Am I able to edit those captions or maybe
Oh
somewhere
yeah,
in the
yeah, for
shorter
sure.
sentences or
So
something like that?
yep, if you hit edit, you can say, okay, I want to shorten this. I want to add my own thing. If something was wrong, you can change it in here and save it. You can even like translate text if you want to change everything to French or something. It'll um, translate the entire thing to French. So you can do that if for some reason you need that. But it's a kind of just a you have the ability to edit those, yeah, anytime you need. So anytime you accept it, hit edit, and then you can do that way. Yeah, thanks.
Thanks.
Um, So now we've got our first delta table, right? This DOI species raw table. So what do we want to do with it? So the first thing we can do is like we've been working in Python in this notebook so far, but with just this little percent %SQL, or you could change it in this drop down right here too. You can write super simple or super complex SQL queries on top of your data. Like this is a relatively complex one with CT common table expression CTEs that basically says it uses some spatial SQL in here to do make sure that the polygon is contained on the globe because some of them weren't. So again, some data cleaning things. Um, Make sure that in the globe, do a bunch of like string parsing to faster than you can do it from a geospatial way. You can do string processing to turn these multi-polygons into an array of polygons. So we can run this to create another table, which is our WKT array table. So again, you just hop over and kind of see this happening in real time. We go from this raw table to our DOI species WKT array table, where instead of like one giant multi-polygon, now we have our array of individual polygons. So obviously these are super duper 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 long, right? But we've got those now in place in an array of individual polygons. Fantastic. Now let's pivot and say, hey, we don't want to write SQL anymore. We want to do this in PySpark. So the exact same table that we just wrote out that you can pass between these cells in your notebook, you can all of a sudden go from writing SQL to writing Python or PySpark on it. So if you're familiar with PySpark, you can say it's the same thing as saying, I'm just reading this table. I'm adding a column here, which explodes out the array into an individual row for each one of the array elements. Um, and we're doing a couple other things I want to touch on as well. But you can just see that this is essentially like your SQL query, but you're writing it in PySpark now, and you're doing it on the exact same data. So just showing the versatility, going back and forth to whatever is easiest in that case. But what I want
Justin,
to,
sorry, a quick
yeah,
question
yeah.
on that versatility from the chat. So if I want to use other open source geospatial libraries, how do I leverage those in these notebooks and do I install them? Kind of what does that look like for you?
Yep. Yeah. So a lot of it is pip install. So if we go back up to the top, like we pip installed Shapely and this one I'm about to use and GeoPandas. So it's like the pip install is notebook specific in this case. So, pip install, the rest of the notebook has access to those. And what we're doing right here, actually is a good time for that question, is we're using Spark UDF here, which is just like a Python function with this little UDF decorator that utilizes the WKT functionality of Shapely to say, hey, we're going to load this and then dump this out to make sure that this is a properly formatted polygon as we go, right? To kind of do a validation of polygon. So essentially what you're able to do is to use Spark on all of your standard geospatial libraries by either just doing it single threaded as you would normally, or by wrapping it in this UDF, in which you can now use this as like almost a built-in Spark function here. So you're saying with column WKT polygon, I'm going to validate those, and that's running this Shapely command, which normally is single-threaded, but is now operating in distributed in parallel using Spark. This
Gotcha.
next, yeah, this next example here is using one of the built-in H3 commands. So this covers the entire polygon with H3 hexagons. and then saves this as another table, which is our H3 array. So again, we can, if we run that, we can hop over and look at our H3 array. And in this case, like we said, we exploded out the array of polygons. So each row is now an individual polygon. And each one has a array cover of all the H3 indexes that sit on top of that polygon to make the full coverage. And then finally, you can work with SQL. And so we did SQL first, then we did PySpark, and now you can work with SQL and PySpark at the same time. Where essentially you can write a SQL query and run Spark SQL with that query, and you could add things like with column blah 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 blah, and do any other functionality you want on top of that as well. So it's like pairing writing SQL queries to also writing the PySpark. So you just have that ability to do all three as part of that. So we finally, this is the table that's going to fuel our app, create this DOI species explode table. We actually explode out all of the H3 indexes. So we can do what Databricks is really good at and work with really large data sets. So in this case, we've got literally one H3, like our species name here has every single H3 index that included in that coverage polygon as an individual row. So we can go back and pull out these really quickly as we go through. And finally, we won't get into this too much because I know we don't have a ton of time, but we also liquid cluster our table. So you can think of the way a lot of times these delta tables in Parquet and traditionally stored is partitioned, which makes it part of what makes it really fast, like being columnar makes it fast. I mean, things are stored in columns. But also the fact that it's you can partition on things like we could partition on species, we could partition on date or that kind of thing to make it so you're only, when you run a query, you're only looking at the files necessary to fulfill that query. So this is how you can have trillion row tables and still have fast queries, is that it knows to just look in the partition that you're looking at, which is in like a where clause. However, those can be difficult to manage partitions. They can grow and shrink in size. You want to have like good distribution across your partitions in terms of like the size of the files. And that can be cumbersome and difficult to do, especially over time. Like you make your decision on partitioning, you don't know what to do in the future. So in this case, Databricks has something called liquid clustering, where instead of having to decide partitioning and Z ordering and that kind of thing, you can just say cluster by and have the things that you're often filtering on. So things like H3 and com name, which is your species name, you end up filtering by those. And another thing I wanted to show is we say, oh no, we run this and we have a syntax error near com name. What do we do to fix this? So built in, like from a Gen AI perspective, we have this diagnose error button. So if you are in a Databricks notebook and you want to diagnose the error, you can actually get responses to say, what was the error code? Here's some code to fix that. A lot of times it fixes in place. I didn't do it this time, but you can have it fixed in place that way. And take this and say, oh, I forgot my parentheses around this. So if I wanted to liquid cluster by these columns, is actually in these parentheses. So it's just a little bit of that to kind of show you why, like some of the stuff that's added on is in these notebooks as opposed to just standard Jupyter notebooks, right? Additionally, you can generate code here where if you wanted to just go straight up, tell me what you want me to do, you could say like, write a SQL query to pull com name from my, species explode table, right? It'll actually like generate code for you, right? I don't have a species explode because I gave it the wrong name, but you know what I mean. You can accept this and then run it, and you can do your code generation here right within your notebook, which is kind of cool. And then finally, the last thing I'm going to show you from a notebook standpoint is we have the ability to visualize our data in the notebook, same way you would in a Jupyter notebook. So we can run our query here, which is like saying pick where American crocodile. Do a little bit of data manipulation, import your Kepler GL here, and look at the polygon. And then actually, let's see, I think I clicked that twice by accident. See, I know in a live demo, it always, so I have the,
And just the time check, Justin, we have about, I think, 10 minutes left. So it
yeah,
might
I'll hop
be
past this, but you can essentially get your, map directly in line in your notebook the same way you would any other kind. So the other things I want to kind of cover now that we've gone through the notebook and like how working in this notebook would normally happen. Um, what I want to touch on is one, we already kind of shown how the SQL editor, how you can come over here and write the same queries that you're running in your notebook in a SQL editor and get the same type of thing. So this is like your select where American crocodile um, query that you can run. And this is like for people who are used to writing in SQL, used to working in databases that way. And then we'll touch on Databricks apps. So if you come in here under compute, we have our clusters that we're running on. We're running this on a lab cluster. You can look at exactly like the specs on that and create new clusters as you want to, create new SQL warehouses. You can also come over here to apps, right? And this is our species coverage map. You can see that we've got our environment for our app, like all of our environment variables, packages that are installed, the logs from running our app are all right here. We can look at our deployments and our source code for the application is just as simple as this. So again, this is, like I said, this is a Plotly Dash app. So we have our requirements here, which are the Python packages we need installed. Our environment is declared in our app.yaml. And then the entire app is contained in this app.py. Right, so what this is just wrapping Kepler GL and Plotly Dash and running it that way. So when we do deploy it, and deploying is as simple as like hitting the deploy button, you can see it prepares the source code and like goes through and it only takes about a minute to stop the app and bring it back up again. But I can hop over to this app right here and say, this is all of our data that was like super hard to deal with, all H3 indexed and built upon an application here. You can see the number of species that go over each one of these hexagons is the count. And select the species from the drop-down map above. That we can still do that same thing where we say like, okay, I want my American crocodile. Um, run that, and it goes and retrieves the H3, the polygon, and actually hits one of our foundation models. So like Llama 3.3, 70B, to give you a description of the American crocodile here. And does that for each one of these. And you can fully interact and zoom in and look at the polygon that was passed back for this in addition to the description and say I can really quickly bounce back and forth to all of these. So if I wanted to do the American alligator instead of the American crocodile, it'll just take a second to pull all the hexes, those polygons, and then display with you along with your description that's generated on the fly for each one of these species that exist in the list. And finally, the last thing I do before I'll open up for questions or for additional questions, right, is how I talked about orchestration and automation a lot. So what I want to touch on here is workflows and how it's super duper easy to take the things that we just did in these notebooks and actually create workflows and jobs out of them that can be triggered by new data landing in a location, by timing. Say, I want to run this every hour, I want to run this once a day at 1 a.m. every day. It's as simple as taking a notebook that you've written, like our download data notebook points to that one where we're downloading the data. And our process massive multi-polygons takes us to the other one that we're looking at. So you can see here, this links directly to the notebook that we are just working in. And basically what it does is it says run this notebook, and then once this is done, do this one. And we can pass parameters from one job to the other. So I give it the catalog and schema values here. And this job reads it from the previous job. All that's there if you need to. If you want to add other tasks along the way, you can do Python scripts, additional notebooks. You can do SQL queries. You can mix and match all of these you want to orchestrate as complex of a workflow like diagram as you need to do all this stuff. And when you do that, you can observe every single run that was run and look at, okay, this was run successfully. I want to see exactly what our notebook looks like that was run as part of that run and what maybe any intermediate results are. Um, this one's loading kind of slowly, of course. But you can look at the results across all of these whenever you need to, including ones that air out, right? So if one air out, you can see, okay, it actually aired out on whatever cell of the, so here you go. You can see what happened with whatever specific cell aired out of that workflow. So just kind of showing, here you go, here's the output, right? So you can see check, 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 check. It all worked fine. Versus ones that did fail, you can look at specifically what cell of that run failed at what point in the notebook. So just some things I want to highlight. I know we've got about 4 minutes left, so I'll kind of open it up for questions now.
Thanks, Justin. Fantastic demonstration. Really liked the alligator and crocodile habitats. Got a couple of questions coming in. I guess the first one that might be good to answer is across all of the different tools and apps you showed today. So, does Databricks do the governance for me through all of those? What kind of options do we have if we want to make sure that we're respecting governance across all the tools and giving certain people access? What does that look like?
Yep, no, it's a really good question. So you can think of essentially every asset that exists within Databricks is governed through Unity Catalog. And
Yeah,
you can think of that um, from like conceptually the idea of where this catalog page, right? So we've got our catalog within each three-level namespace. So your catalog, your schema, and your tables or volumes or whatever. Each one of these, as we go into like a specific table, has permissions that you can set, grant specific permissions to either certain groups, certain individuals in Databricks to do any of these things on it, right? And it's not just for tables as you would in like any other thing. It's like I said, volume. So your cloud storage, as opposed to saying I have to create some kind of crazy S3 policy to include and exclude people, right? This essentially is pointing to cloud storage, but it's permissioned the same way as the tables are. Additionally, if you have ML models, right, they can be permissions on your models the exact same way too. So these are all managed through MLflow. And you
right.
can same thing, you grant or revoke access to those. Model serving endpoints, you can grant and revoke access to model serving endpoints the same way. So you can think of it as every single like asset in Databricks is governed through Unity Catalog in a very similar way.
Yeah, that makes a lot of sense, and I think that's kind of where the question was going. For artificial intelligence specifically, I know that some of our users are interested in the gateway. I don't know if you use that for your application, but it might be worth giving a brief touch on that for what you were just showing.
Yeah, so AI Gateway specifically, it's specifically for LLMs. So I can show you exactly what it is. So if you want to serve, so we have, you can serve any and every and any ML model you have. Additionally, you can serve arbitrary Python functions if you want to. But we have a certain set of foundation models, like your llama models, your embedding models that you might have. And let's look at the details here. So if you're looking at serving up LLM, either one that you fine-tuned or one that's part of the foundation model that you want served just for yourself, you can come to serving, create serving endpoint, and select an entity. So in this case, the foundation model, you can point to OpenAI, Bedrock, our internal Llama models, confirm
Yeah.
that.
It looks like
And
looks like you can take Unity catalog stuff there too.
yes. Oh, yeah. So you, from a Unity catalog perspective, these are all your models that you've trained. So you can serve your uh,
Right.
like my Justin, models of I've got, Justin M dot whatever where my models are, my BART classifier, my churn model, my travel model, those types of things that are traditional models as well. But AI Gateway specifically, so you can serve those models. AI Gateway as a product works on putting guardrails for input and output safety and PII detection, that kind of stuff on LLM serving stuff. So instead of just saying, hey, we're going to throw whatever you want in or out of this LLM, you can have those guardrails around each one of those as well.
Very cool.
Yeah.
Thanks, Justin. I think if there are other questions that come up, we are happy to answer them over email. Or via the chat. I know Keenan just put the email to set up a trial. If anyone's interested in exploring Databricks and getting your hands dirty, you can just send an email to that Databricks email that Keenan put in the chat, Federal Sandbox, and we'll get you situated. But thanks again, Justin. Really cool, informative demonstration. Did you have anything you wanted to touch on this slide?
I don't think so. This is just kind of like if you guys want the QR code just to bring the email back up,
Yeah,
something like that. Here it is.
awesome. Well, I love the app. Keenan, Nick, did you have anything to add or any follow-up questions for our friend Justin here?
No, great demo, Justin. Thanks to the attendees from DOI and all the good questions. We have more of these events, which those who register will get access to. Um, Look forward to more conversations around our GIS capabilities and let everyone get back to their day. Thanks all. Have a good day.